Okay, so there's only a few, like 2 people in here right now.
I don't know why.
I was afraid I was gonna be late because like when I was taking the interstate, there was a traffic jam.
I see. Alright, good morning. This is today's attendance question. We are calculating a surface area. I'm trying to graph the two so we kind of have a visualization of what's going on. But this is a little weird. I don't know why is that changing to an equation instead of functions. But both of them are two variable function. When you face this kind of question, you have to remember which one are we calculating, which one were just a constraint. This question says we want to find surface area of the path cut from the paraboloid. So z equal to minus x squared minus y squared is the one we will be focused on. You need to know which function, obviously this was correct, which function that we're supposed to take different when you were calculating surface area. So let me try to review the surface area calculation formula. And we were trying to follow the formula as closely as possible. I want to make sure we're doing the right thing, especially when the question itself involves multiple functions. Like this one, you're facing this multivariable function that's also multivariable function, and then both of them representing a three-dimensional surface. So we have to be careful to concentrate on which one are we supposed to calculate. Now, since the surface is from this paraboloid, this is the one we are applying for the formula. Our surface area formula is this: surface area is equal to a double integral of square root of 1 plus fx, partial derivative of the function f will be, right now, the f will be the 2 minus x squared minus y squared. So that's the f we're focusing. fx squared plus fy squared, but partial derivative in x squared, partial derivative in y squared. And then dA, it's a double integral, so it's double integral, so we have to do dA instead of dx or dy. We do have to figure out what was the integration region in order to find the proper integration order. Okay. So at least at the beginning, we focus on identifying the right formula and then try to know what we're supposed to follow. So in this chart, when you're applying the formula for the surface area calculation, make sure it's ready. For example, we certainly want to make sure that we have the right derivative. This is the surface equation, so that will be the surface function. Now, the partial derivative of x is equal to derivative in x is negative 2x. Then the partial derivative in y will be at y. That will be negative 2y. So knowing that we now have our integration function, we have not specify the integration region. Let's try to be clear which stage are we on. So far we've been having this surface area calculation of a double integration of square root of both of the partial derivative has to be squared. So it'll be 1 plus, whenever you square a negative number, they become positive number, so it's going to be 4x squared. And we squared this partial derivative, have 4y squared. Okay, so that's our integration function. And this is again a double integral. All right, now time to think about integration region. The way we can determine the right integration limit, because we're going to do iterated integral, is to identify what kind of integration it is. If it's a square, a rectangle, a triangle, or parallelogram, Most of the time, if that's the case, we'll apply rectangular coordinate system. If you have a circular integration region, you might as well use a polar coordinate. So we're gonna try to look at what exactly is the integration region. That's why I'm trying to draw the three-dimensional figure of the two. You see, we have a cone intersecting a paraboloid. Of surface is paraboloid. This is a cone. As I was trying to enter, it becomes weirder and weirder in this picture. At least it's kind of indicating the image. All right, so we're gonna try to put our own understanding of it. Obviously, the top surface will be the one represented by the paraboloid. See, something is opening down. This, my visual graph sound perfect. So this is a paraboloid, and this one again will make a three figures. So that's a paraboloid presented by the top, and this one is a cone. So it opens this way. It's cone. And then of course they certainly are intersecting. But the line of intersection is this drawing. This is the line of intersection of the two. All right, and then we're trying to find the surface at the top. So that's the cap of the cap cut by the cone is like a cutter. But this is maybe this the top part of it, only the cap part of the paraboloid. So you can see what's the integration region. It will be the edge, which is that circle projecting onto the xy plane. In this case, here is our x axis, y axis, and this is our z axis to there. So you have to find the intersection between the two surfaces in order to identify the proper, like this is the integration region. So essentially, we're projecting this onto the xy plane, this x value, y value. So the line of intersection is very necessary. So we are pairing these two equations together. So you have z equal to 2 minus x squared minus y squared. And then we have z equal to square root of x squared plus y squared. And what are the other? That looks like a circle. I'm trying to think about. Right. So how do we go forward? Obviously, we have to pair these two equations together. They both equal to z, and all the point at the intersection are point that satisfy this equation and this equation. Pairing this together, we realize that we have to have x squared plus y squared. All I'm doing right now is that you got a double integral to do, and then what kind of integration region that we have. All I'm doing is try to find a proper integration region. And my intention or the visualization of it looks like it got to be a circle. Well, what kind of circle? Like, what is the radius of circle? We got to do that. So setting this equation, you can put this equation because that's how you determine intersection between two surfaces. So this is 2 minus x squared. This is actually x squared and y squared. You can write it as x squared plus y squared. So this is actually the same as this. Kind of write it that way. So why am I doing this? Because I realized I gotta calculate a radius. And if it's a circular region, then x equal to, we know the routine. If you do a polar coordinate, you have a circular integration region, then x equal to r cosine theta. Use some of the common formula, y equal to r sine theta. And also, if you have x squared plus y squared, it will equal to r squared because of Pythagorean theorem, or because of the trig identity, this square plus this square equals r squared. Another equation is if you have square roots. So you have square root of x squared plus y squared, square root of r squared, which equal to r. Right? That would apply quickly to what we're doing now. And you're going to have r equal to 2 minus r squared. All I'm doing is try to find the radius r. So move this over, you have r squared plus r. We move everything to the left side equation, minus 2, this equal to 0. And then we can factor this into r minus 1 times r plus 2. So then we have a solution that says r equal to 1. I mean, the second part is saying r plus 2, right? But r plus 2, it means r equal to negative 2. But obviously, we don't want a negative radius, so that one do not work. So r equal to 1 will be the case, and then this radius is 1. Okay, so project that onto the xy plane, you see a circular integration region. This integration region, we are going to do full component. Now this integration for the surface area now becomes a little bit clear. So we slowly go from the original equation surface area from something that we know the integration function, but now integration region from. Now we know the integration region is a circular integration region of radius 1. So we go the thetas from 0 to 2 pi because the full circle, and then the radius from 0 to 1. This is square root of 1 plus x squared plus y squared equal r squared. So this 4x squared plus 4y squared is actually 4r squared, 4r squared. And then the dA in polar coordinate two-dimensional notation in polar coordinate dA equal to dr d theta. Okay, so this is everything set up. The integration limit set up, the integration order is there. Normally we do dr d theta rather than d theta dr. So that's everything that we had, and then the rest is all calculation or whatever you were able to calculate this one. Common method will be when you have a complex. Let's say the integration order can definitely be separated. So this is a number, okay? On the outside, 0 to 2 pi d theta, that's a number. Integration 0 to 2 pi d theta equal to 2 pi. So we're basically having a 2 pi multiplied by this integration. For this integration, you might want to do a substitution method just so the integration can be done smoothly. U equal to 1 plus 4r squared, and then the du will equal to 8r dr, because the derivative of 4r squared is 8r, but then this is the differential. Differential is the derivative time the differential variables times the dr. So this is indicating that whenever you have rdr, like we have here rdr, the rdr is actually equal to 1 over 8 du. So that'll make sure that we can smoothly transition from the integration variable r to integration variable of u. So we have root of u, and then there's 1 over 8, and there's du. Of course, there's the integration. But finish the integration, and then we're probably going to revert back to the integration variable. So integration of this is u to the 1/2 power. Applying the power of the integration, you have 1 over 8 u to the power 1/2 plus 1 is 3/2 power, and then this is 3/2. Okay, this simplify into 4 times 8 divided by 2 is 4, and 4 times 8 is 4 to the 12. So 1 over 12 u to the power 3/2. What is power? U. What is u? U is 1 plus 4r squared, and then we still have the power 3/2. Let's finish the antiderivative with playing integration limit. The integration limit is 0 to 1, so 0 and 1. So that should allow you to figure out the value for the inner integral. The value for the outer integral is 2 pi. So I think that's pretty much the whole calculation part. I had the whole picture. This is the calculation. I hope that you finish the rest of the simplified. 3/2 power is actually root. So let's continue. Maybe you already had the answer. Sometimes that gets a little bit naggy. I made it longer than necessary. So if you already have the answer, you can now submit it. If you don't have the answer, I can wait for you to finish the calculation. Okay, if we go back to the calculation, it's here. I mean, even the choices are still there. Okay, okay. Thank you. Please take some notes. I realize that in the class, for the most part of the class time, I'm the one writing the books. But as a student, you're supposed to write notes as well. I mean, when I was in college, I write all the time. Even when I was half asleep, I'm still taking notes because that's what's keeping me awake most of the time. I have to write something so I'm not falling asleep. I have many classes per semester, so I have that tendency to fall asleep in the middle of class too. So I decided, number one, I'll sit in the front, so I will scare myself, so that way I will fall asleep. Number two, I take notes no matter what's happening on the board, I write it down. So I'm a persistent note taker. But it works, at least as far as keeping one person awake, and also by the end of each semester, my notes is everywhere. People will borrow the notes so they can review. Okay. So I'm the kind of people that feel like if you work hard, if you keep thinking and writing, eventually you get the idea, no matter how complicated it is. Right, anyone else?
I'm still trying to solve this, so.
Okay. Here are the calculation. I haven't really finished the calculation. If you want to continue from here, we'll bring the number. If you put 1, then 4 times 1 is 1, so 1 plus 4 is 5. So we have 1 over 12, 5 to the power of 1.5 power. Is 1.5 power. It's 5 over 5. And then this is minus 5 when you're plugging the number 0, it will be 1 to subtract 1. All right, this is the inner integration. The outer integration will give you a 2 pi. This integrate, this will be 2 pi. So this whole calculation is this number times 2 pi. All right, and then to extend a little bit further, you have 6 pi, that's 1 over pi over 6. The 12 cancel the 2, so it's pi over 6 multiplied by, then here we have, this is a 5 to the 3 half power. 5 to the power 3 is 125. So it's root of 125 minus 1. I mean, root of 125 can be simplified into 5 root 5. So it should be like 5 root 5 minus 1, and then multiply by pi over 6 if we simplify. So anyway, I think the final answer is this one or this one. Let's see if we find it. Oops. Right. And then you probably see the correct answer. If you have the wrong one, it could be the simplification. So it's pi over 6, not pi over 12. You might want to double check your calculation. I mean, these answers are similar to each other, so try to differentiate them. Okay. If you accidentally have the wrong one earlier, make sure you change it because A and C are very, very similar. So I think it's possible that we have students that actually choose A instead of C. It should be C. Okay. Anyone else? I think for everyone in class, if you submitted the wrong answer, I can immediately tell you. But if you choose the wrong one, online, I will be able to tell you because I mean not have your attention at the moment. Right. As you can see, if you have that is wrong because we multiply 2 pi, so the 2 will cancel the 12. The 2 over 12 is 1 over 6. That's why we have denominator equal to 6, not 12. So check your work. Okay, that's today's attendance question. Do you have any question from the homework that you want to talk about before we move on? Any question over homework that we had so far? Section 1 to 5. Any questions? Remember to correct your answer. It should be C. If you have A, you might want to double check your calculation. I did try to finish it up. And the coefficient should be pi over 6, not pi over 12. Right. If you are online, if you have any question, you can type it in the chat, or you can put on the speaker, and then you can speak, even if it's even if you're not in the classroom. You'll speak and ask questions. Any homework questions? So we're okay so far. All right. If there's nobody asked any questions, she'll say one student. Okay. So I'll keep it open there. Well, yesterday was long the whole time. Okay. Now, what we do today, we're going to move on to section 6. If you have any question from the homework on the first few sections, we can go over that. If not, let's see. Today we're going to talk about 13.6. Right, they are, oh, I already have it downloaded. So here we are. So what is 13.6? The title is triple integration. So we're moving on, instead of double integral, we're moving on to 3 variables. So instead of variable x and y, now we're going to have x, y, and z. So we're going to use triple integration to solve problems such as volume calculation, center of mass. So that's really the focus of this section. So we're going to start with calculation and terminology and notation. Then we're moving on to apply triple integration for volume and center of mass calculation. All right. So number one is we should be able, we should realize that we can calculate volume between two surfaces by using the top surface minus the bottom surface. But this has a certain requirement that the top surface, the higher surface, fxy, has to be larger than the bottom one. So z equal to f of x. And z equal to g of xy, z equal to fxy, z equal to g of xy. It's two different functions. One represents a surface that's higher. The other one represents the g function represents a surface that's lower. So if you want to find the volume between these two surfaces, you can use a double integral like what's written in here. So a double integration of xy minus g of x. So basically, it's top surface minus bottom surface. What it does is the top surface minus bottom surface give you the height of the individual bar, and then the dA give you the base area of the bar. So fx minus g of x times dA is a miniature volume calculation. So one dimension, the z dimension, time the x dimension, time the y dimension, all three multiplied 3-dimensional measure, and then all these miniature volume calculation added all together is a total volume. And those addition is a continuous addition, which is why we would do integration. Right? This is something that can be understood from 13.2. In 13.2, we say that we could calculate volume below a surface using a double integral. Now the fxy, gxy are the surface representing the height. So if you have a bigger volume, subtract the lower volume, of course you will find volume in between, which is the reason why this formula will work. However, we can move further than this. So this is one of the questions that we had to illustrate that this works and triple integration also works. What is this question? This question says we have two planes. One plane is the plane says equal to 3xy 3x plus y minus 4, which is at -4 when xy equals 0. So that will be the lower surface. So z equals 3x, I guess I could. Z equals 3x plus y minus 4. Because x minus 4 is the purple one. At the z-axis, it reaches a -4. That's why I know that one is this plane. And then the top plane is the second equation, which goes z equal to 8 minus 3x minus 2y. So when x equals 0, y equals 0, z equals 8. So that's 8 on the z-axis to reach a higher point. The question says we want to find the volume between these two in the first octant. What do we mean by first octant? We mean x is positive, y is positive, and z is also positive. That's what we want. Okay, so when we do that in the first octant, okay, so this is showing the entire plane. The picture on the left showing the whole plane intersecting. The plane on the right is showing exactly what volume are we calculating. Okay, only by the plane. Okay, first octant, isn't that means x is positive, y is positive, z is positive. But in here, the part of z is negative. Anyway, so what our intention will go is like we are limiting that x being positive, y is positive, and the z is not. Z has its top boundary, that's that red region, the red plane, and the purple plane is the bottom plane. So as far as the z value, this is the top, and this is the bottom, the higher one and the lower one. So we try to follow this formula there. We want to take the higher surface minus lower surface and then integrate that and in that triangular integration region that we see in this picture. So that was the intention. So now here is the question. We want to be able to use a proper integration to do this calculation. In here, the whole solution's already in here, but what will be the proper process of this? I guess I should start from the beginning to explain the logic. Okay, so this entire picture, obviously we can write the calculation from the beginning. Okay, so you see, this one is the top one. That's this one. Okay, so in that equation, give the equation of the surface, which is the surface plane, and then the bottom one is this one. And I represent the purple region that we see here. So according to what we have in this volume, the gray volume in between these two surfaces, this volume calculation should be able to calculate by, we will do a double integral and double integral the top surface, which is this one. So you're going to take the 8 minus 3x minus 2y, the top surface, minus the bottom surface, minus those 3x plus y minus 4, and then dA. So if we follow the formula that we see in the text closely, like follow this really closely, you'll be, the first thing is you will identify what is at the top, what at the bottom. That's why the visualization is very useful. And then it doesn't tell you what was the integration region, and that could be the problem. So in the text just went through this really fast and solutions already out there. But I want to explain how do we get that integration region identified. Okay, so when you see this, it looks like we have to integrate with respect to the variable x or y. So the dA part has to be identified. So maybe are we going to calculate the dA? It's a triangular region, so the triangular region to be, we identify that, and you will identify what exactly is this line. right? I identify that line and project it onto the XY plane because the A will be integrated over a variable X and variable Y. So you can project the whole thing to see how it looks like on the XY plane. And that will form a triangle kind of like this on the XY plane. This is our X, this is our Y. That's our integration region. That's the integration region there. So to know how to calculate it, we have to have proper integration region for the double integral. And this is a part that was hard in the triple integration because sometimes the integration region are not clearly stated. So what we're gonna do is look at this line I'm drawing. It's a line of intersection between the two. So at the line of intersection, one of the things that we should realize that because of the line of intersection, any point of x, y, z of these two have to have the same z, have the same x and same y. So this x, y, and z will have to follow both of these equations. So g equal to a minus 3x minus 2y. We're going to pair these equations together to find out the proper equation, this equation. Okay. So we pair this together, this intersection of these two lines is a line. A line is infinite, so expanded. That's why I try to draw over there, project it onto the xy plane. So we set equal, and of course, in the equation about x, y, is the projection we wish to find. So in the line of intersection projecting onto the xy plane, there's no more z value. So we will pair these two together, and we'll go maybe type there. Okay, so we write it out. The first equation is a minus 3x minus 2y. The second equation is 3x plus y and minus 4. So that's it. That's the line of intersection projected onto the xy plane. It's a relation between x and y that this equation have to follow without consideration of the z value, because on the xy plane, there's no more z. Or you can say z equal to 0 to be exact. So, we will just future out the z value relation from the intersection line. And now we have this to move this all to one side of the equation to identify the relation. I guess we move all the negative terms to the right side of the equation. You have 8 equal to 3x, 3x is 6x. Y plus 2y is 3y. And then there's still minus 4. Try to simplify this equation. And then we can move the 4 to the other side of the equation, and we have 12 equal to 6x plus 3y. And then there's common factor of 3. So we divide both sides of the equation by 3. Then we have 4 equal to 2x plus y. There. Right, and then we can determine that we're gonna do dy dx or we're gonna do dx dy. I guess a better choice will be, since y can be isolated, y equal to 4 minus 2x. That will be the upper boundary for the y value. Think about this integration region. This is a line. This equation we just find out is a line that you see. This is the y equal to 4 minus 2x. Okay, so this will be the 4, and this will be a 2, and that's 0. So x goes from, so we can go dy dx, dy dx, and then here x is from 0 to 2. The y is from 0 to, this is a y value, but the top edge of the triangle, 4 minus 2x. So that's an analysis that we might be able to talk through about identifying the proper integration region for the volume calculation. And the rest of them, we simplify this into 12. I mean, all these calculations are not for nothing. You move it over, it's a 12 minus 6x and then minus 3y. So that's going to be our integration function. You see similar things in there as well. So now we have the whole double integral for the volume calculation down, and go back, see the solution. The rest of the calculation, I guess, is now it's not difficult to do. Right, identify the 0 to 2 and 0 to 4 minus 2x as the upper boundary, integrate this function. So if you integrate this, you can see 12by is 12y minus 6xy, and then 3y negative 3y integrated into negative 3y square root 2. Plug in upper limit and lower limit and integrate with respect to x. Because the process does take a few steps for finishing the calculation part. Any question? I hope that kind of explained the reasoning about identifying the integration limit. Normally, after we know the integration, the rest is integration steps following the power rule. Any question? So this is the example illustrating that this formula does work as far as finding the volume. However, when we think about this, what can we look at this? You can think of this as this a minus 3x minus 2x can be considered as the upper limit for the v value, and then the other equation plain v equals 3x plus y minus 4 is the lower limit for the v value. So you can think of this two number as the upper limit, lower limit for the dz. So this integration will give you the top surface minus lower surface also. So you can think of this calculation also based on the triple integral. So that brings out the idea triple integral can be applied as volume calculation. Just like the double integral can be applied for area calculation. Okay, so let's try to review what we were talking about. What is a triple integral? We're going to talk about iterated integration to do triple integral. So if you have triple integral, it's kind of like the in the name, you're going to integrate 3 times. You're going to have an inner integral, a middle integral, and an outer integral. It's going to have 3 layers of integration. It's iterated, so therefore you have to finish the inner integral before integrate in the middle integral before you can integrate the outer integral. So it has to go by steps. If you mess up the order, sometimes the integration limit has to change. Sometimes the calculation might be wrong. So let's talk about the theory. The volume calculation can that we see in here can be considered as triple integration dv. This is when your integration of number 1. So if you don't have integration function in there, you just plain integrating over this 3-dimensional region that we call D. D is a 3-dimensional region, and you triple integrate over D without any function, without variable. Then this is the integration of 1, triple integral 1 dv will allow you to calculate volume. Assuming that we're able to find the proper boundary of the surface that's outside this volume. Okay, so here we have, this is the integration order that we find in here. So we follow the integration order dz, dy, dx. Now, part of the difficulty in triple integral is what will be the appropriate integration order. Now that we have 3 variables, unlike before, with double integral, we have only two variables, dx, dy, or dy, dx. There's no others. So maybe one is better than the other one, but there's only 2 that we can choose from. So now we have 3. Just think about permutating of 3 elements in complementary is 3 P3, right? So it's 3 times 2 times 1, 6 is different ordering if you have 3 letters. So the order of integration for triple integral, there's 3 different options, 6 options. So which one we do? Normally we pick the one that's most intuitive, most easy to understand. So but occasionally if we run into calculation difficulty, we might switch integration over just so it would be easier to do. Now, the first one we go through is following the dv, dy, dx. So that's just, that is assuming you have a clear understanding what will be the top surface, what will be the bottom surface. That's our DZ. So it's highest Z value and lowest Z value that represent the top surface and bottom surface. And then the other integration variables are dy dx. That is you project your surface onto the xy plane. This can be changed. You can do dz dy dx, or you can do dz dx dy. Either way, z is your inner integration. That's assuming that we have a very clear top and bottom surface. So then the rest of the integration boundary is to look at y and x, which one has a numerical boundary, which one has a variable boundary, depending on the shape of the projection onto the xy plane. And this is the integration. So we can evaluate it if the proper surface, the proper boundary can be identified. Okay, this is going back to the Riemann sum definition of the volume. The volume calculation can be considered as limit of a many small volume calculation. And that's why this can be extended further as a triple integral. You think of you can dissect the whole volume calculation to many small cube. Every cube is the volume is dx dy delta x times delta y times delta z. Have many of those small volume calculation added all together when the region, or when d goes to 0, when each of these volumes become really small, the limit value of that is actually an integration, a continuous version of summation is integration. So this is the reason why we could use triple integral for the volume calculation. And let's look at the example. Okay. This is an example of the volume calculation. And again, this one can be calculated with double integral, but we extend it onto the triple integral. And also we want to practice identifying integration limit using this example. This is a pyramid right next to the axis plane. So here we want to find the volume of the space region in the first octant bounded by the plane z equal to 2 minus y over 2 minus 2x minus 3. That's our equation of the surface right there. It's a plane. Using the order of the integration d dy dx. Set up the triple integral that gives the volume in the other 5 order of the integration. So we're trying all 6. That's the intention. So I'm going to start the first one with dz dy dx. Right here, the picture is already drawn. Now, if you want to use dz as your inner integration, then dy dx should be the yz plane that you projected on. So here we already have the picture. This is a surface representing z equal to 2 minus y over 3 minus 2x over 3. We have 2 right there. And also we see the other 2 number can also be determined. For example, on the zx plane, it will the y equal to 0. So z equal to 2 minus 2x over 3. So this one is 3. Okay, that's x equal to 3 because 2 minus 2 times 0 over 3 equal to 0. It's this intersection. Over here, this one is on the yz plane. On the yz plane is when x equal to 0. So z equal to 2 minus y over 3. So y equal to 6. When y equal to 6, z equal to 0. That's 2, that was 6. So all these, the angle, what's that? The vertex of triangle can be quickly identified by laying one of the coordinate point, one of the x coordinate, y coordinate equal to 0. That's how we identify. Anyway, we project it onto the xy plane. That's what's on the right side, because that way we can identify the integration limit for y and x. So we're going to start with the first one. In this equation, this picture already displayed, the z the bottom, this is the volume factor, is the one on the left shows the volume that we want to calculate. The smallest value for z is 0. The highest value for z is on that surface. So z is go from 0 to, okay, z is from 0 to the surface formula. Surface is z equal to y over, z equal to 2 minus y over 3 minus 2x over 3. So that's our boundary for z, integration limit for z. And then going further, this is our z. The next thing is we want to find the boundary for y and for x. We should identify the x first because x has a numerical boundary. It's not too hard to tell it. From this, you can see the x is from 0 to 3. That's 3. Or when you are letting z equal to 0, it will be 0 equal to 2 minus right, projected onto the, yeah. So I think I write it over here. Did I? No, right, yeah. Okay, so this is a process. The inner integration is, this is the surface, the top, these from 0 to 2 minus y over 3 minus 2x over 3. But then you want to identify the boundary for x and the, now identify that one. So this equation with the z equal to 0 is y equal to 6 minus 2x. So then from that you can find out x equal to 3 is the x intercept. So that was 3. 0 to 3 is the boundary for x. And then for the y, the dy, we have the y formula, y equal to 6 minus 2x. That's from the projection of the projection on the xy plane. But this is the equation. So y, smallest y is on this line, biggest one on this line. And this line is y equal to 6 minus 2x. Okay, so this is the first order, dz, dy, dx. If we move up the order, this is the calculation part. If we change the integration order, let's say we want to do dz, dx, dy. Then again, you need to look at its projection onto the xy plane. This line represents y equal to 6 minus 2x. So if you identify the x, so the x value on this line will be x equal to 3 minus y over 2. So that's how we know the upper limit for the upper limit value for the upper limit of the integration for x. And the x is from 0 to 3 minus y over 2. The outer integration is y variable. From the projection from this image, you can see the y values from 0 to 6. Or from this equation, y equal to 6 minus 2x. So the highest y value is 6 and lowest is at 0. So this is our second order of operation. Another one is what if we want to do dx, dy, dz. So if you switch the order of operation, you have to identify what will be the projection and what will be the upper limit and lower limit. So number one thing is if we want to do dx, dy, dz, so you're projecting the surface onto the xz plane, onto the yz plane. So z equal to 2 minus y over 2 minus 2x over 3 is our surface. If we project this onto the yz plane, then x equal to 0. So that x value ultimately is 0 on the yz plane, and you have z equal to 2 minus y over 3. And solving for we need to solve for the y value. Solve for the y value, we have 6 minus 3z. We have to solve for the y because we need to know the upper limit on the integration limit for y. So that 6 minus 3z is what we have there. That's the process determining the integration limit for y. On the outside is dz. The outer integration of dz, all we have to know is what's the proper boundary for z value. You can see it's 0 from 0 to 2. 0 to 2 is how we determine. So by looking at the projection onto the yz plane, we're able to find out the integration limit for z and y. Z is the numerical boundary, y is a variable boundary, functional boundary, because we see what I was drawing that arrow to say where the arrow meets the bottom z value and the highest z value. Actually, it was y value, isn't it? Yeah, z is from 0 to 2. For a given z value, I should be doing this way, this arrow. So I guess the arrow is wrong. Okay, that was that process. How do we go from dx, dy, dz? About the x boundary. X is from 0 to the surface. So you will take this surface and try to solve the x value from it. So take that surface equation and try to figure out a way to solve for the x. You move the 2x over 3 to the right, to the left, and then move the z to the right. Switch the x and z, and then try to multiply both side equation by 3. That's the second step. And finally, we have the x value. After you solve the x value from the surface, this x value is our upper boundary for the integration limit of dx. So it's the x boundary. So now we have finished all three, the dy, dz, and the dx. That's how you identify proper integration limit in a triple integral if the surface is given. Now moving on, and this is to summarize what we've done so far. We've done dz, dx, dy, dx, dy, dz, and dx, dz, dy. Lastly, let's try to look at one more. We can also do dy, dz, dx. This one, I try to look at the surface from the beginning. So we're trying to find the volume below that surface. So you see the surface equation right here. If you look at the integration order, we have to project this surface onto, you see, to project it onto the zx plane. But let's first identify the upper boundary for y value. Lower boundary certainly is 0 as you look at it. The upper boundary is on that surface. So what do? We have to solve the y value from the surface equation. So here we are. We're gonna try to isolate the y value and move the z over to the right and solve for the y. And then multiply both side equation by 3. That's our upper boundary. So this is how the y upper limit of integration for dy. So that's how we. So those are in our integration already done. And moving on, you gotta try to project your surface onto the xz plane. So how do we do that? Project surface equation onto the xz plane. What you can do is on the xz plane, y equals 0. So with that equation, say when you make y equals 0, you have z equal to 2 minus 2x over 3, and that's the projection. This is an xz plane I'm drawing. So it's a triangular integration region as well. So now from that integration region, we want to identify the vertical boundary for x. You see the x is from 0 to 3. So on the outside, we will write 0 to 3. Okay, on the other hand, we need a variable boundary for the z. So we're solving z equal to 2 minus x over 3. We need to have the z value, but z is already solved. I solved z from here. So that's the upper boundary for the z, right? If you want to switch it, for example, if you want to do dy, dx, dz, then you have to solve the x from the equation from z equal to 2 minus x over 3. You're going to solve the x if you intend to do dy, dx, if you want to switch the integration order again. So I hope that working in detail on how we look at the determination of the integration limit, we will be able to find out some pattern or some reason or some way to handle it. Because very often people know or kind of have a feeling what should be the integration limit, but they end up having the wrong thing there because they didn't sit down and look at which variable we're focusing on. So that's that one. All right. I've been talking about projection, but sometimes we still have some issue projecting onto a plane, XY plane, YZ plane, or XZ plane. So here we have a question. When you have two surfaces, the two surfaces intersect, causes you to form a curve. If you were just intersecting to a plane, the intersection is a line. But if you have a curved surface, it's intersecting a plane, then the intersection will also be a curve. So this question says, consider the surface z equals 3 minus x squared minus y squared, and the plane z equal to y, which is showing the picture. The plane is this orange one, and then the purple one is the surface. So the curve of their intersection is shown in an image. we want to find the equation of the projection into the coordinate plane. There's three coordinate plane, xy plane, start with xy plane. So if we look at the intersection at the intersection, it's a curve, it's three-dimensional curve, but we're not looking at that curve. We're trying to projecting that curve onto the xy plane. Let's start with projection onto the xy plane. So in that projection, what we do is the points of the intersection have to satisfy both of these two equations. But when they project it onto the xy plane, we no longer have any relation about the z value. So what you're going to do, you combine these two equations and summarize that into an equation of x and y. That's how you project onto xy plane. So all I have to do is pair these two equations together. You end up having 2y equals 3 minus x1 minus y squared. You can then move the x or y squared to the left side. You have x squared plus y squared plus 2y equals 3. Because the summation of square, this is the equation of circle in the xy plane. If we can even find the center of circle if we complete the squares. So that's the projection onto the xy plane. All right, if we try to project it onto the yz plane, meaning that we are going to find equation relation related with x and y. So if it's projecting onto the yz plane, you see the three-dimensional picture. If you project this piece of curve, the purple one, onto the yz plane, okay, so it will follow the same curve, same relation. So this equation, z equal to 2y already is representing relation between x and relation between y and z. We don't care about what is the relation with x-axis because it's not going to be shown in the yz plane anyway. So that's that projection. Lastly, when I see the projection into the xz plane, so essentially in the xz plane, all you're capable of representing is relation between the x coordinate and y coordinate. So we're not making y equal to 0. We're combining these two equations to eventually removing or substituting the y variable. So what we're going to do is from the second equation, y equals z over 2, you plug into the first equation, which you're moving the y by z over 2. And then we end up having the equation of z and x. And that is showing up based on this curve. Inside this curve, what is the relation between x and z? And that is the projection onto the xz plane of a curve. And this ends up being an ellipse because it's summation of square, but the coefficient is different. So there is summation of square, sometimes it's a circle, sometimes it's an ellipse, depending on whether the ratio of the two square is 1:1. All right. Then in the textbook, these are the solution. The projection onto the xy plane is a circle with radius 2. So we even go as far as determining the center of circle. The projection onto the xz plane is an ellipse. It was this, same as what we have here, but after combining and completing the circle, completing the square, we have this is an ellipse, equation of ellipse. And in the yz plane, it's still same, it's still a plane. So it's a line actually. If we talk about inside the projection inside the plane, it is a line inside the yz plane. So this is about how do we identify a relation between two variables after they were projected onto the coordinate plane. All right, let's move on to another example of volume calculation. Also, we're a little bit more on how we switch integration order. So this question, we were calculating volume between these three surfaces. The bottom surface is a circle. Okay, this is not a bottom surface. This is a cylinder. X squared plus y squared equal to 1. Inside the xy plane is a circle, but three-dimensionally, x squared plus y squared is missing the z variable, so it's representing a cylinder. X squared plus y squared is a cylinder that you see the purple bar in the image. Z equal to 0 is a plane, so xy plane is bottom plane. Z equal to negative y is a red one that you see in the image. It's a slanted plane. So z equal to 0 the plane, z equal to negative y the plane. Now x squared plus y squared 1 is a cylinder. So the plane intersecting the other plane and then intersecting the cylinder. And all three surfaces causing us to form a inside part of the space. That's the volume that we try to calculate. All right, let's see how do we calculate this volume with triple integral. We were with order of integration dz dy dx or dy dx or dx dz dy. Change the order operation, whichever one, which we will figure out the total volume. Right, start with the first order of operation. So if we want to do dz dy dx, okay. So number one, we want to identify what would be proper boundary for z. So what is a higher surface? What's the bottom surface? So you can see the top surface obviously is this one. This is z equal to negative 1. It's a plane at the top of it. This looks like a piece of watermelon. Okay, so this is a top plane, and there's a bottom plane. So the top plane is equal to negative y. The bottom plane is equal to 0. Is the xy plane. So I put down 0 for z equal to 0 and z equal to negative y. That's the top plane and the bottom plane for the whole surface. All right, moving on, and let's project this onto the xy plane. So we are gonna look at if we project the whole thing onto the xy plane, what does it look like? Okay, I specifically try to copy over the image. The projection onto the xy plane is actually a circle. Inside the xy plane, x squared plus y squared is a circle, so the region inside the circle, inside a half circle. You see the positive y values over here on the right. So these are all negative y value inside that region. So from there, we are trying to identify what would be the proper number for x. Okay, we need the number for x. You can see x over here, negative, positive 1, negative 1, x is between negative 1 and positive 1. So the outer integration is x variable, so we need numerical number for x. So all you have to do is identify highest x and lowest x. That's done for the dx boundary for the integration limit for x. So now we have integration limit for z, integration limit for x. Let's look at integration limit for y. Okay, so what do we do? The y value, I kind of draw the arrow from lower y to the upper y. The y is a function. So the upper y is this line. So x-axis is y equal to 0. The lower y is actually a bottom circle of the. So you have a circle, but then we only have negative y value. So x is from negative 1 to positive 1, but the y is this. So the y value actually goes from, if you give an x value and then the y value is this. So on the negative circle there. So on the equation of the circle, x squared plus y squared equal to 1 is the equation of the circle, also equation of the cylinder. You solve for the y value, then y squared equal to 1 minus x squared, take square root both side equation, but we only want the negative y value. It's negative. Also, you see the equal to negative y is high because y has to be negative. Negative y is positive z. So we know that z gotta be a negative number. So negative root of 1 minus x squared is the lower y value. The top y value is at 0. So those determination of integration limit for y. Any question? Okay. So once we have the integration limit, all we have to do is finish the integration. Right, so here are the integration once we identify proper boundary for z, for y, for x. Those are all the integration limit over there. That's the integration that we identify over here. Now, this dz, since the integration function is 1, this integration gave us negative y. Then the y dy will give us negative y squared over 2. Plug in the integration limit. With the lower limit, you get negative. The negative cancel, minus negative 1 times positive 1 half. 1 minus x squared dx. And then we apply power over integration. And then the final answer for the volume is 2 over 3. So that finished this calculation volume using the first order operation to do dz dy dx. I went through all these examples in the hope that we will have a freedom choose whatever integration order that we decide to use. Now let's look at the second scenario. Second one, we're choosing the integration order that is the dy dx dz. So how do we do this? Number one, I want to determine the integration limit for dy. So we need to know the highest y value and lowest y value. You see the y-axis over here. This is our y-axis. So parallel to the y-axis, you can say the smallest y value is over on the left, going through the edge, going through the surface, x squared plus y squared equal to 1. The top y value going through the surface is applying v equal to negative y. So from v equal to negative y, we can turn around, find the y value that's negative z. Z equal negative z from the equation. So from this surface, we have x squared plus y squared equal 1, and then solve for the y value. Remember, y squared equal to 1 minus x squared. You take the negative y equal to negative, we go 1 minus. So from the equation x squared plus y squared 1, we're solving the negative y value. So negative root 1 minus x squared is our lower limit for y value. So basically, looking at a surface, we should try to identify a proper formula for the y value at any given surface at the highest y and lowest y. So that's for the inner integration. We really go to the surface, the exact surface, to know which surface provided that y value. All right, moving on. We have to project this whole thing onto the xz plane. So how do we project this onto the xz plane? We have to kind of combine that intersection. So if you look at the xz plane, this is the bottom edge. If you project the bottom edge onto the x-plane, it will be at the x-axis. Okay, and then this is the top edge. And we want to know if that curve will project onto the x-plane, how does it project? I think it's still another circle. So how does that curve being represented? That curve is x squared plus y squared plus 1, which is a cylinder, intersecting the z with negative y. So this surface intersecting this surface. So then we're gonna pair them together. Then z equal to negative y. So the y is negative z. So the x squared plus z squared equal to 1. That is a projection of this curve projecting into xz plane. So it's end up being a half circle, but it's a positive half circle of z value, positive z value. So the z value in that circle, z goes from 0 to 1. So by drawing that circle, identify the equation of the projection of that curve, we realize it's a circle. Region inside the circle is our integration region. So half circle integration region. So z from 0 to 1. Next, we need to know the integration boundary for x. Z is from 0 to 1, and then the x value go from, we need to know the lowest x value and the upper x value. This is the lower edge on the left. This is the upper edge on the right. So we need to find the x value from the equation of the circle, x equal to plus or minus the root of 1 minus x squared. So at the upper limit is positive, lower limit is negative. So dx, the integration limit for x is from negative root of 1 minus c squared to the positive root of 1 minus c squared. So these are the determination process when we try to figure out what will be the proper integration order and integration limit. So with this, you can finish the calculation, provide the same answer as what we have there. This is definitely the easiest way to do. Also, integration order should provide the same answer, but this will give us an idea on how to determine the right way for the integration calculation. Okay, so combining all that, and then we end up having this. This is what's in the text. Trying to explain how this one can be decided one by one. In the text, it's overall, this is what we have. So it doesn't explain some of the idea or reason why we determine that way. Okay. Okay, a couple of properties for triple integral, many of them are the same. If you have integration region, this is 3-dimensional integration region now. For double integral, we have 2-dimensional integration region. For a single integration, we have integration that region that was an interval. So they're all kind of different from one another. So if you have 3-dimensional integration region, that can be partitioned into two non-overlapping parts. So D1, D2 are disjoint. Suppose D equal to D1 union D2, then the integration can be calculated also individually. So if you want to find the volume of the D, all you have to do is find the volume of D1 and then plus volume D2. So this triple integral can be added together. So that is in relation to the volume, like this volume plus this volume equal to total volume, assuming they are not overlapping. If they're all overlapping, that'll be a different story. All right, so this is the reason that we need this because we have this example. So here we have a question. We want to find the volume of the space region bounded by the coordinate plane, which means x plane, y-z plane, xy plane, and zx plane, xz plane. There's three coordinate plane here. The one at the bottom, the one on that side, the one on that side. Three coordinate plane. Bounded by the coordinate plane and by z equal to 1 minus x over 2. There is a cylinder without y-axis, just like this one over here. And the other one is z equal to 1 minus y over 2. That's this cylinder, this plane. So these are two planes bounded this side. So this is kind of like a pyramid. This pyramid has 1, 2, 3, and then 2 of these 5 sides. So 5-sided cylinder. Or you can also consider that one at the base, 4 at the side. We want to set up a triple integral to find the volume D in all 6 orders of integration. Okay, so sometime we may have to do a summation. If we were doing dz, dy, dx, we definitely have to do a summation. So we separate them into R1 and R2. Projection on these two are different. So we look at these two separately, then this one like it's on this side, the z equal to 1 minus 1 half x will be the top surface. While on this side, z equal to 1 minus 1/4 y will be the top surface. So they were looking at two volume calculation there. So top minus bottom, so that's integration limit for z, the first integration for the R1. If R2 is a base and this is a top, and then the z equal to 0 is the bottom. So there we have it. So this is the second one. This is the first one. This is the z equal to 1 minus x over 2 surface. This is z equal to 1 minus y2 y4 surface. Both of them should have triangular integration region, but the integration region is R1 and R2. R1, R2 is in this image there, right? And then the integration, that's the integration order using dz, dy, dx. Any question? Or if you look at that image, we can choose other integration order. The reason that we have to do two separate integration is because we choose to do the integration order of dy, dz, dy, dx. That's the reason it end up being two separate integral. Okay, but we could choose the integration order in a way that is easier for computation. For example, we do not project onto xy plane, project onto y plane, and the integration we will be able to finish the integration as one integral instead of two separate ones. Okay, so if we project this onto the YZ, this is this line will be the projection onto the YZ plane. That's naturally the boundary there. So we can do integration of this little YZ, and we can do dz, dy, and then the inner one will be dx. Do it this way, and then our integration will be y value, and you can see the y value is 0 to 4. I'm going to change the integration order there. And then for the z, we already have this equation, right? Z is this way. So z is going from 0 to 1 minus 1 over 4y. So that will be our integration limit for the z value because it was the value of the upper line. And then lastly is the x value. X goes from this is our x-axis. Lower x is on this side. Upper x is this side. So the lower x is in the y plane, so it's 0. But the upper x is in here. So you see that surface represented by this equation of z equal to 1 minus x over 2. This surface, we can solve for the x value. We're looking for boundary of the x value. So d equal to 1 minus x over 2. And then the x over 2 bring to the left side, which equals 1 minus z. And then we multiply both sides by 2x equal to 2 minus 2z. That will be the upper limit to the. And because all these sides are parallel, there's no additional integration we need to do. So if we are projecting the entire thing onto the volume, onto the YV plane, we will be able to calculate a whole volume calculation with a single triple integration. And so that shows that different integration order presents a different level of difficulty as far as calculation and different ways to solve it. But the final answer should be the same. That's it for today. I hope that kind of give us some idea on how to handle triple integral, and we'll talk about more examples tomorrow. That's it for today. Thank you.